Hello and welcome back to Precalculus. The section for today is 3.5 on exponential growth and decay, modeling, data modeling, right? The word problems. By far my favorite, um, because it's just so useful and it's um, everywhere, right? We have already seen the problem of taking a loan, like a car loan. Pretty much all of the loans work the same way, where you have that equation. But before we get into all of those equations, we can categorize them all into two groups, right? There is a growth group, which will have k positive, and the graphs would look like this. This is time, usually. And then there will be decay group, where k is negative, and the graphs would look like this. Again, this is time axis. Now, the y-axis could be anything. Could be money, could be, we'll see, mass, and a whole bunch of other stuff. So, all of these are going to be for equation y equals a e to the k t, which is your exponential model. Exponential model. Now, clearly, growth, right? The name says the values that you are observing are growing in time. And then decay are the ones that decay, where you lose stuff over time. So for the growth model, you can look into population, for instance. Population in general grows over time. We have explosion of human population. We doubled our population since 1973, I believe, or whatever. We doubled the population on the planet since that time, right? And you have, let's say, growth of money in the account due to interest, or growth of, right, the money because there was a loan given at certain percent, and then that loan, right, gets the loan that you took, let's say on 10,000, over time will grow to add interest, right? Because interest is a service that you pay because someone lends you the money. Just like when you, right, you pay mechanic to fix your car, you pay for a room rental when you go to a hotel, right? You pay for an item that you're purchasing. Well, if you borrow the money, that's a service that someone, right, is willing to give, so that you can buy something that you would otherwise not be able to buy at all. So you take a loan. Your credit cards as well. Every time you swipe the credit card, you are technically borrowing money from the bank, which is why, right? Think about it, swiping the credit card on something that is $5, because you really need to pay interest service fee on $5, right? First of all, whatever you're buying, do you really need it? Because generally it's like $5, most likely you don't. But the thing is that, right, the credit card, even though it has your name on it, it is not your money. It's bank's money, right? We're talking about a credit card. I'm not talking about a debit card where you put the money in a bank and it's your money. I'm talking about a credit card, which is the bank's money. They give you the limit for spending, 1,000, 5,000, 20,000, right? Or that black card that has no spending limit. And they give you money, and they say you can swipe this card anywhere, right? And every time you swipe, you actually um, borrow that money from the bank, and then you have to pay it back. So if you swipe something for $5, you have to um, pay those $5 back, and usually 20% interest, right? Generally, credit cards are like anywhere from 16 to 20 And then if you have those terrible retail cards, like those are insanely bad, like 30%. So you buy something that's like $100 and it's instantly 130 on your or what you have to pay back. Like those retail cards are absolute the worst menace that you can take, because if you look at the percent, they're all like 29 something, 30, even 31. I've seen they offered me a card, I believe a Goodyear card for tires. I think they offered me a credit card and say, if you open the credit card, then you get this and get this and get this. And I just turned around and I said, you see the 31%? So everything that you told me that I get, right, is actually in value less than the 31% that I'm going to pay, right? So when you know mathematics, when you understand the growth and decay and all these kind of things, right, the life becomes so easy. Um, and obviously, if you don't, right, you get cheated on all the refinancing and all the other schemes that are there. They look good, and then you always lose out on the long run, because no one would put a scheme where you are the winner and they are the losers, right? It's always they have to win. So there you go. The other thing is the decay, which is the loss of some kind, and generally you can think about, let's say, decay of garbage. That's one of the big ecological issues, right? That the plastic is not decomposing, so we try to recycle and do all of these things to reduce the footprint on the environment. Um, so decay of garbage is, you're going to have one of the plastic shopping bags, right, decaying like 10,000 years before it's completely reabsorbed, not completely reabsorbed, but 10,000 years for it to be somewhat reabsorbed by the um, environment. So we have those huge issues, but then you also have the nuclear stuff, right? That is also taking a very long time to decay. But then you also have metabolizing drug in the body, which is again another decay problem, which is why we have the dosage, right? You take a pill every 2 hours, every 4 hours, every 6 hours, or once a day, twice a day, whatever, right? The dosing is calculated through what is called the biological half-life, and some stuff that you guys get to um, compute in that field if you work in the pharmaceutical field. So carbon dating is another one for history, right? Where you take a look at the isotope of carbon, C14, and you see how many are decayed, right, from the atom, and then you figure out how old something is. We're going to do all of those problems. It's a lot of fun for this particular lecture. And as I said, we were going to have a part two of this next class as well, because we just have a lot of different cool things to look at. And then one equation that goes both ways, right? Because generally you just wanna see money grow. You don't wanna you don't invest money hoping that to lose it, right? You don't deposit garbage in one spot and bury it hoping it will grow, right? You want it to decay. So pretty much everything that I told you so far, like you wanted to see go one way, right? Um, but then you have this concept of heating and cooling, which is called Newton's law of cooling. Well, that one, right? Sometimes you need one, sometimes you need the other. So that's kind of a cool one that swings both ways, which is again something that we can take a look at. And this calculation is so awesome that you can literally compute down to a minute of how much you need to, let's say, put your chicken or turkey or something in the oven, just or a cake, and just walk away. And when it says ding, it's going to be perfect at that temperature. Right? My students actually in calculus and differential equations did these for their projects at home, and some were baking chicken, some were baking cakes and cookies and whatever, right? But the trick is that uh, you can compute down to a second of how long do you need to leave your um, whatever is in the oven right? And compute when to take it out. So we'll see that as well, right? Because all of that stuff is pre-calculus calculations that get upgraded later in calculus and differential equations to some um, higher concepts. But everything starts now. This is like the introductory lecture for everything. And all of those problems, as you can see, are in this y equals a e to the kt. So all of the growth problems, like money and population, are going to have positive k's, and all the decay problems, which is like loss of mass and so on, are going to have negative k's in our calculations. So to open the calculations here, I'm going to again take a look at the $10,000 loan at 3% for let's go 4 years, so then it's not all threes. So 4 years, right? And since I'm not giving you compounding, like last time, we're gonna say continuous. So we can use the E, right? So we did, when we did 3.1, you should go and review. We did the compounding monthly for a car payment, right? And then we did show continuous at the end very briefly. But now I just want to say, okay, some kind of loan. Because when you compound continuously, you are going to get absolutely maximum return. And if you compound monthly or anything else, it will be less money than what we are going to compute now. So this calculation is the easiest, fastest, and it gives you the absolute maximum for payments. So if you and then it doesn't matter if the bank is compounding daily, monthly, annually, semi-annually, weekly. You just don't care, because if you have the money to pay for the highest possible one, then all of the other ones below will have less, in which case you don't have to worry about any of those. So we said that the amount is equal to principal e to the RT. Well, that's the same equation as up there, except we just change the letters, right? But A is the amount, P is the principal, R is rate in decimal, not in a percent, and then T is time in years. But we have all of these numbers. We just need to plug them in. So you have your 10,000 E 0.03 times 4 years, right? So you can plug this in your calculator. This is going to be 10,000 times E raised to the 0.12. And this goes, right, if you have TI 83, 84, right, you put all of this in one shot in your calculator. If not, you will obviously compute this first and then times 10,000. So 0.12. So I'm getting that the amount you owe back is $11,274.97. That's the money you owe back. Right? So if you borrow 10,000 for your loan at 3% for 4 years, right? And I don't care what that is. Is it a school loan? Is it a car loan? It is just you wanted to take $10,000 just to feel you're rich, whatever. Um, you have you have to return, right, 11, like over time, right, over those 4 years you have to return the 11,274 and 97 cents. Now you might be interested, so what's my monthly payment? Well, that's easy, right? You have 48 payments in 4 years. So monthly payment, MPT, is going to be 11,274 and 9 said 4 and 97 cents divided by 48 payments. And that is another calculation that you get to do. So divided by 48, there we go. 234, come on tablet, you can do it. 234 0.90, right? When you round properly, you have to put 2 decimals. Obviously, we're talking money, right? And when you do this calculation, you see that this type of a loan for 4 years, you will be paying back 234.90. So this is something. Now, let's say you decide to go to a very, very expensive school. You didn't do any community service while you were RV. You did not build your portfolio of any kind. You don't have any extracurriculars. So no scholarship for you, obviously, right? And you want to go to a school that it's like 70,000 a year, and you don't have any of that money, so you're just going to take loan for $140,000. Great. $140,000, let's say at 2% for 20 years. So I want you to repeat the calculation we just did for these numbers and get me the monthly payment, which you will have to pay every month for 20 years, right, after you graduate. And I'm going to go get the new cooling pad. Did anyone compute the monthly payment? Anyone?
I got the formula, but my calculator doesn't have an E button, so I wasn't able to solve it.
Well, why don't you use a cell phone? If you take the calculator on a cell phone and turn the cell phone sideways, you can get the E button on the cell phone. And I
An
know
iPhone
that
has an.
even Apple can do that now.
Let me go grab my phone. I'll be right back.
Okay. 100. Okay, so 140,000 times E raised to the 0.4.
I got a really big number.
Exactly. And 20 years times 12 is 240 payments. And that's your monthly payment, right? $870. Now, if they're compounding monthly and so on, this is just gonna go down like $2-3, and if they compound monthly. So these are the loan problems. And as I said, we had those also done in a greater detail when we had the compounding with n equals 12, right? So please review those, and we can actually do one or two next class to review as well after everything is done. So compounding formula was A equals P 1 plus R over N raised to the NT. So that was done last time when we did 3.1. All right, so what are the type of problems that we want to look into now? Well, we have these decay problems, which will involve something called half-life, but I want to actually work out, since last time we did population and this, right? I want to work out now the temperature problem, which is the Newton's law of cooling, since we did the other growth problems. Newton's law of cooling. So Newton's law of cooling, as I said, goes both ways. It's used to heat up and to cool off materials. And the equation that is generally given to you on exams, because you will learn this equation and how to derive it in differential equations. Sometimes some people even do it in calculus too. So, it is an equation where you have the C, which is temperature of the room, temperature, actually. How about room temperature? There we go, room temperature. So C is the room temperature. T0 is initial temperature. I'll explain what is that for. And T is the temperature of the object. And then you have your T, lowercase t, which is time. Now that's minutes, hours, right, depending on your application. Generally, right, if you're baking something, you want to do everything in minutes, and then you can convert those minutes into hours. Also, if your
Fire.
coffee is cooling, right, you're not going to wait 7 hours for the coffee to cool or tea to cool, right? So it could be done in minutes. Yes, go ahead.
What's the difference between initial temp and temperature? Oh, is it saying initial temperature of? Wait, yeah. What's the difference between initial temperature and temperature of the object?
So both are the temperatures of the object. Now, the initial temperature of the object is at the beginning of your calculation, in the beginning
Oh,
of the measurement. So let's say you want to bake a chicken, right? And that chicken was sitting on a counter, and it's now at 70 degrees, because that was, the temperature in the kitchen was 70 degrees, and the chicken reached 70 degrees because it was sitting there marinated or whatever, right? Now, the chicken is going into the oven, right? Oven is at, let's say, 400 degrees. So the room temperature for the chicken is 400 degrees because it's going into the oven, which is the room, right? And it's 400 degrees. The initial temperature of the chicken is 70 because that's the starting temperature for the problem. And then you have a target temperature, which is this big T, which is 165 for poultry, right, for chicken, to be considered fully cooked and safe for consumption, is 165 Fahrenheit. So you have three temperatures at play. Initial temperature is just the starting temperature, like coffee. Your coffee could be, let's say, at 115 degrees when you just brew it, right? And it's now sitting in the cup. You're not gonna drink it, right? At 115, 120 degrees. Right? Well, it will burn you. So that's your initial temperature of the coffee, and then you wait, and because the coffee is sitting in a room that has lower temperature, the heat will dissipate, right? And the coffee will cool down, trying to meet and equal the room temperature. So the coffee will be cooling down towards the temperature of the room. So let's say your room is 70 degrees, so the coffee will try over long period of time to reach that 70 degrees. Now you consume it before that happens, right? You consume the coffee when it's like 100 and something degrees, right? Because we know that our body temperature is like mid 90s, right? So anything that it's a little bit warmer than mid 90s, we feel it as hot, and it get hotter and hotter and hotter, and anything that it's lower than that. So I think that proposed chilling temperature for, let's say, soda beverages or so on is like 36 degrees, which is, freezing temperatures like 32. So that's kind of really, really cold. And then you have like the wine and so on is like 50 degrees, right, to keep the wine from spoiling and to be perfectly, I don't know. There are temperatures along the way that you can discover. So when you're dealing with Newton's law of cooling, you have to figure out first: are you heating the object up, or are you cooling it down? And in general, I let's put the chicken in the oven, and this is actually something that you can do tomorrow for like $5-6. You can buy the full uncooked, cleaned chicken, right? In ShopRite, let's say, for like $6, $5-6, the whole chicken. And then you can actually do this experiment risking the $6, right? And if it works, hey, it's dinner for everyone, right? It's it's a really cool thing, right? And that's without you even knowing, right? And all of these kind of things. So let's take a look at the calculation. I clearly have my exponential equation there. There is the exponential piece. I have a whole bunch of these other things. So what kind of calculations do I need to do here? Well, first of all, let's set some parameters for the problem. So oven is going to be at 400 degrees. Target temperature has to be 165 degrees. That's not Celsius, sorry, Fahrenheit. I'm used to Celsius, obviously. So oven at the 400 degrees, and the target temperature for the chicken at the end is 165, which is the safe temperature. We're gonna say initial temperature for the chicken is, let's call it 70 degrees, right? Because let's say it was sitting on a kitchen counter for like 2 hours because you don't have cats, and marinating in whatever. So initial temperature is 70 degrees, and you are wondering how long do you need to bake, right? Now you might have some questions now. Well, how about the size of the chicken? Will that impact? How about the dish that I'm using, right? One with the tall walls, one with the low walls, one is made out of iron, the other one is made out of aluminum, that tray that you can buy for like $2-3 also with the chicken. So like if you don't have anything to bake the chicken in, you can just buy the disposable one in the store, and like chicken plus the tray would, and plus whatever seasoning, would all cost you $10, right, for the full dinner. You can toss in like a bag of peas or something like that for $1.50, and yeah, there is the dinner, right? So when you look at all of this, right, you say, well, is there a difference between size of the chicken, type of the dish that I'm using, like the pan or whatever? Is there a difference between the gas oven versus electric oven versus wood fire oven? Maybe maybe you're burning wood to do this. And the answer is yes. But all of that information is going to be mushed together in this K that you will compute. So you don't have to worry about those individual discrepancies between like two different cooking sessions. because you will have to determine this K for every cooking session, because you will be using different dish or different size. Like even if you're using the same oven every time, right? Your K is still going to change because your chicken is going to be a different size, your pan is going to be different size, the amount of seasoning you're using is going to be different, right? So the heat penetration is going to be different. So this K is always going to change from problem to problem, which is why you have to have the intermediate measurement with that temperature probe, right? The one that has a spike and a temperature gauge on the top. You have to stab it into the chicken, let's say 30 minutes into baking, because you need that reference point to calculate K. Now let's see. So oven is at 400 degrees. That's going to be the room temperature for the chicken. The initial temperature T0 is 70. That's good for a chicken. The target temperature is there. And then if you try to plug all of this into the equation, you quickly see that you have two variables, right? You don't know K and you don't know T. So this information is not enough for you, right? You need more information, and that's the information that, say, 30 minutes into baking, check the temperature of the chicken, and let's say you got T equals 30 minutes, temperature of the chicken was, let's say, 89 degrees. It's too slow. Whatever, doesn't matter. Doesn't matter. It's it's gonna be something. So how about 90 to have a round, nice round number? There we go, 90 degrees. It will be something. You read it on the scale. Well, cool. We have our equation, right? Temperature is equal to room temperature plus, and then you have the difference between the initial temperature and the room temperature. And you have e to the kt. Right, so that's your equation. That's actually T0 minus, I said it correctly and I wrote it backwards. I don't know why. There we go. So now I am going to use this information here first so I can calculate K. Because as I said, you and I are going to get different temperature here. If we start our experiment, like every single one of you and me, right? So we have how many people on the call? 9. 8 students and me, right? So if everyone is to do this experiment, we are all going to have a different size chicken, different type of the oven, different type of a pan, different type of seasoning, right? So we are going to have different temperature here after 30 minutes. So this is why that's individual data, which will give you your individual Ks. I'm just doing the general example as like one of us would have. All right, so the temperature is 90. The room temperature for the chicken is 400 degrees. The initial temperature for the chicken going in is 70. 400 degrees again. E to the K times 30 minutes for time. So this is me using 30, 70, right, which is T and T, point, to figure out K. Because if you look at this equation, the only unknown variable is K. So that's negative 310 is equal to negative 330 e to the 30k. I just moved 400, right, subtracted 400, and then 70 minus 400. So now, when I divide both sides, you see basic exponential equation here. That's basic equation. So, divide both sides by negative 330, and these zeros will drop. So 31 divided by 33 is 0.939393. So I'm just going to put 4. Here is me using 4 decimals, right? and e to the 30k. Now we learned in the last section, hit both sides with ln. That will kill off e. So I have ln of the previous answer, which is on the left-hand side, negative 0.06252 equals to 30k. Guys, note that I have 4 digits, which we call significant digits. I did not say 4 decimal places. I said 4 significant digits. This one is not significant and it doesn't count. So 4 non-zero digits after whatever amount of zeros you have in front. And now all I need to do to calculate my k is to divide this number by 30 and again keep 4 significant digits. Negative 0.00, those are not significant. And then we have 2084. 2084. See, 4 significant digits here. So we don't count these, the string of zeros. And this is the k that pertains to this particular situation. So my temperature is, right, for the problem, 400 plus 700 minus 400 as E, and then to the negative 0.002084 T. That's it. So now, if I want to calculate the time, and I know that my target temperature is 165, I just need to run this calculation again to calculate T. My target temperature is 165. I have all of the other numbers, and that will give me the time for cooking. So minus 165, that's going to be negative 235 is equal to negative 330 E negative 0.002084 T. Divide both sides by 330, and then those negatives will drop. So we have 235 divided by 330, 0.7121 is equal to this. And then what we learned in the last lesson, hit both sides by ln to kill the e. So on the left, when you put ln of 0.7 and right, you will get negative 0.3395. And on the right hand side, you have negative 0.002084 T. Divide the two numbers. And get T equals 162.9 minutes. So you can call that 163 minutes. Since you already did 30 minutes calculation to measure, right? You already did baking because, so this is the total time, and then minus 30 is what is left for cooking, which is 2 hours and 13 minutes left. Now, why did I subtract 30 here? Because you can do this calculation after you do your 30-minute measurement. You can't do any of this work until you're already 30 minutes into cooking, right? So you put the chicken in, close the oven, and set your cell phone to beep in 30 minutes. When your cell phone beeps in 30 minutes, you go and you use that temperature probe to come up with a temperature for the chicken, right? And that's going to be 30 minutes already into baking. Then you get to do your calculation for K, right? Because remember, the K calculation here took the 70, sorry, this was 90, not 70, 90. 30 minutes in, 90 degrees temperature when you, right, 70 was initial temperature going into. So for 30 minutes, the temperature went up 20 degrees, right? So you put the chicken in, and then in 30 minutes, once you have this measurement of 30 minutes in 90 degrees, you can plug all of those numbers into equation to use exponential equation that we just learned and calculate your K. That gives you what we call mathematical model. This over here is called math model. Mathematical model. And now you can ask yourself, how long do I need to wait for the chicken to be 165? Or maybe you want 170, maybe you want 175. Maybe you want to burn it to the char, 300 degrees, right? See how long will it take for it to burn completely, right? So that will depend on your, right, what you want after that. So whatever, or you can plug in the time. Let's say, what if I bake chicken for 300 minutes? Well, you plug in 300 here and it will spit out the temperature on the other end. So you can either feed in the desired temperature to see how long will it take you to reach it, or you can say, if I bake this for 2 hours, which is 120 minutes, what would the temperature be? And you will see it's less than 165, not safe for consumption, right? Beef is the only one that you can, right, eat rare. Pretty much nothing else. I mean, sure, there are other things, but chicken and pork you should definitely not eat undercooked. So, yeah, this is something you can do tomorrow, just for the hell of it, and run this calculation. Set the timer for the time remaining, right? So minus 30, and you will be able to um, have the perfect temperature at the end. So the next class we are going to take a look at all of the decay problems, because what we looked into today was this introductory story, right? And then taking loans, which is growing money. We also took a look at growing the temperature, right? Raising the temperature of the chicken from 70 to 165, right? And that's happening in 163 minutes. And then we also in 3.1 looked at the loan for the car, like we purchased that car. So that's a good example as well. And we did that with compounding as well. So the next day, right, next class, which is on Thursday, we are just going to deal with the decay models and learn about half-life, and then apply that to garbage decay, radioactive decay, metabolizing drug in a body, and right for medications, and so on. Also carbon dating for archaeology and history. So a lot of cool applications there as well. See you on Thursday.